Our final speaker of the day, it may be applicable to Alex as well, is on instant formal expert. Our speaker is Abdelouahab Ayari from Mentor Graphics. He's a digital design and verification solutions application engineer at Mentor Graphics. He has a PhD as an application engineer for formal verification, clock domain crossing, and low power verification. He received his doctorate in formal verification at the University of Freiburg and worked for Micronas GmbH before joining Mentor Graphics. And the topic of the talk this afternoon is instant formal expert. Thank you.
Did you hear me? Okay. So thank you. So the goal of the talk is, of course, not to have all of you experts after the talk, because you are already, or some of you are already experts in formal verification, but at least to give you some details that you can understand formal experts better. And I think if you understand more how formal verification is working, you can do a better job in formal verification. I will do a little bit of background stuff, what is model checking, and the difference to simulation, and why is some design patterns are good for formal verification, others are not good for formal verification. Then I will dig into two technologies: the bound model checking, which is using set solver, and the induction. And at the end, I will show some application where when you are writing for formal verification, when you are writing assertion for formal verification, could be fundamentally different than writing assertion for simulation. So, unfortunately, the talk is a little bit, I have a little bit technical details, so I hope that is fine with you. The goal, of course, is formal verification is to have 100% verification of your design. The formal verification can be seen somehow dual to the simulation. In simulation, you provide RTL and stimulus, and you get, and the simulator tells you what behavior results. In formal verification, you have the RTL, you specify the property or the behavior that you are looking for, and the tool provide you the stimulus. So it's a little bit mysterious, but the tool is who is giving you the stimulus. So, for example, if you're interested to look for bad things, not things that has not to happen in your design, if the tool is failed to find a counterexample to find the stimulus for you, then this is a proof that this bad design, this bad things cannot happen in your design. But if the tool generate stimulus for you, then you have a witness that this bad behavior can or happen in your design. So the formal analysis actually can be split in two parts. The first part is you make some kind of synthesis from the inputs, from the RTL and properties, and later you focus on this, what you have synthesized, and you apply your model checking. So I will not cover the synthesis part here. I will focus more on the model checking. So as I said before, from the RTL and the property, you generate big FSM that is combining both design property logic here. This step is nevertheless very interesting and very important for model checking, because what we are producing is the input for the model checker, and we are interested, of course, to produce efficient, optimal FSM for the property for the model checker. There is a lot of clever ideas and heuristics used in this step. For example, automata theory is used to minimize FSM in this context. So now, going to the model checking, I will explain the model checking based on what we call explicit model checking. This is an approach which is developed in the early of 17s. It is actually today not used anymore, but does not scale. But this approach is very simple, let's say, to use to explain how model checking is working. So let's suppose we have design with 8 states and 2 inputs. The first thing what we have to do is to look to the first, the initial state, and see if the property, given property, hold on it or not. So if this is okay, if the property holds on the initial state, then we make one step further and generate all the next states of the initial state. And for all these generated states, we check again if the property is, let's say, is correct for the states or not. If this is the case, then we proceed again. So we do this in a recursive way. In this procedure, we will not consider states that already have been reached before. And we will stop at the first state that is violating the property. So one thing is actually here to see is that we can go from one state to the next state only if we are done with the first, with the previous, all next previous states. Somehow we are doing, or we are exactly actually doing breadth first search, and before going down to the graph. This approach is guaranteed to terminate because we have a finite state system here. We have a finite number of states, and we are not considering loops. So, and then by the way, this way to go in the breadth before going down, this is what formal verification, what making formal verification exhaustive. So we don't leave any state. We go to all states. So this, as I said before, this is an approach which the first approach used in the 70s for model checking. This is not used anymore today, but does not scale. So one thing that we all always heard is that there is a class of designs that are good for formal verification and another class for designs that are not good for formal verification. I want just to go a little bit here, spend 2 words about what is actually behind this, just to how to say explain what is the reason. And to do this, I have to explain very short, or do or mention very short what does it mean, the complexity here of the model checking. So as you know, or most of you know, that model checking is p-space complete. The runtime is linear in design and exponential in the property size. The algorithms that model checking algorithms is working actually the FSM that we are generating before. So actually, the FSM has what we call a diameter. The diameter of the FSM is the smallest number needed to visit all the states. So if this diameter is actually small, then the model checker will be very effective. If this diameter is actually not small, relatively not small, it's relatively large, actually then model checking will, how to say, will do not a good job. So, or actually will spend more time on this. So, on the first case, we are talking usually from regular structure. FSM are regular structure, but if we have a small diameter, then we are talking about good regular structures. And this is the case when you have, when we are talking about designs that are talking about controls, arbiter, memory controller, and scheduler, and so on and so on and so on. For the other degenerated regular structure, actually we are talking, or the property is actually about portion of the design which is actually doing implicit or explicit counting, and where the counting, the value of the counter have impact on the formal, or where you have a complex data transformation. So actually for this kind of designs, the FSM that you get from the synthesis have a very, very large diameter. So this is why actually we talk, or what we recommend when we go to customer as vendors, we tell, okay, it is actually best suited for designs which are control intensive, and does not mean that it's actually has not to be applied for other kind of designs, but you expect that formal verification will spend more time and need more resources to have to be conclusive in that part. Now, I will go over two technologies, actually because of time. I will just consider these two things, the BMC and induction. So we heard about BMC today in several talks. In BMC, the idea is to give up the notion of proofs and to look for counterexamples up to a design depth n. So in doing this, for example, you don't have to track all the states that you have visited. This makes the approach simpler, but of course, you cannot talk about complete proofs. In this case, you are only talking about bounded proofs. So how is working? So actually, you start with looking for counterexample for one cycle, then for 2 cycles, 3 cycles, and so on and so on. And when you go deeper in the design, the number of states goes exponential. So if in, how to say, doing these steps, you get a counterexample, then you are done. Otherwise, what you can say is actually my assertion, what I'm interested on, is does not have any counterexample within this depth. It is actually bounded proof. That is all what we can say. It is still something that you can tell, but it is up to you to say this is enough or not. But this is what you can tell. You cannot. This is not anymore. This is not a proof. Okay. So how this works actually? So this is the idea of boundary checking, just to look for certain diameter to see how if you have counterexamples there. Now, how this works under the hood? What are most model checking are doing today? So we start with, let's say, suppose we are interested to see if we have counterexample of length 5. So the first thing is we start with the generated FSM, the generated synthesized FSM from the property and design. Then the first thing that we have to do is actually to enfold this FSM 5 times. Then, as next, we will model the inputs and states using Boolean variables that have 0 or 1 as values. So we will remove these states. Now, as we are considering synthesized RTL here, or gate level, these transitions actually, we can assume that these transitions are actually composed or a combination of some gates. We can say, for example, the include or the contains and, nor, and so on and so on. For all these gates, we can write them as Boolean functions. So for every transition that we have, we can collect combine the function, Boolean function that are describing the gates in one big in one big transition formula, or set of clauses, let's say, in the set terminology. So here, every transition that you see here can be translated in a big formula. Now, to mimic the path from initial state to the cycle 5, we have to include all this formula together. So we get an n-path formula from transition 0 to transition 5. So here we end up with a very, very, very large set or very large Boolean function. This is known to how to solve. So there is solver, SAT solver, that can read this piece of formula, this formula, and decide it. And deciding it is actually providing assignments of all the variables involved in this property. The assignment is actually means for every variable that is occurring here, I will give 0, 1 value. And the assignment at the end will be consistent with, how to say, with the network that we have. And the other thing is, as we are enforcing, we are interested to look for counterexamples. So there is a variable called isViolated, and this should be set to 1. So if the SAT solver gives us an assignment that satisfies this property, then we have a counterexample. So this is, in this counterexample, it's actually is built on Boolean formulas. It has not to do a lot of things to do with what we have provided as RTL. But this is actually simple. Then you have to map back this assignments to a counterexample. So this is actually where the mystery is coming from. So there is this is the stimuli that the formula, the model checker are generating. So this is the SAT solver is giving this or generating this assignment, and this is what you are using. So here, one word about the SAT problem. The SAT problem is defined, I think, earlier 70s. Yeah, 70s, and it gained more attention in the around 2000. A lot of work is done in this topic, and the main breakthrough is coming from University of Bristol, and which have developed a tool called Chaff, which have a very clever heuristics and ideas that used to guide how to find solutions in this space. Later, more recently, algorithmic improvement of this of Chaff lead to a solver called Minisat, and today Minisat is actually the de facto SAT solver used in most of commercial tools. So Minisat or SAT solver are actually widely used now and are replacing in large, largely replacing BDDs. Okay. So what we have here is actually, we have in this approach, we don't expect to have proofs. This approach is very effective for finding bugs. We have seen applications that are exhaustive to 30 or even to 100 cycles. This approach is used in a bug hunting way to provide counterexamples found at thousands of sites. Bounded mode checking is maybe good to use when you have a new RTL, because you are expecting to have bugs when you are doing bug hunting, but also if you are doing if you are expecting or happy with bounded proofs. You have some kind of meta reasoning telling you, okay, if there is no counterexample to some depth, then my design is okay. This kind of meta reasoning is outside of the merge checking, and that is your expectation that you are done with this. So now I will move to induction. So induction will give you, so BMC, bound merge checking does not give you counterexample. Induction will give you proofs. So sorry, bounded merge checking does not gives you proofs, but induction will give you proofs. So the idea is actually very simple. It's, everyone has seen this in the school time, and so we have learned in the school that the number of the sum of numbers 1 to n is n times n plus 1 divided by 2. And this property, we have also learned that this property can be proven using the induction principle. So there is this induction principle is split in two cases: the base case and step case. In base case, you have to prove the property holds for n equal 1, and the step case, you have to prove if the property holds for some given natural number k, then it should hold, or you have to prove that it holds at the k plus 1. This is the basic stuff. And the idea is actually to exactly use this kind of induction also for hardware verification, for formal hardware verification. So how this works? Here, one definition. A property is inductive if it holds in the initial state. And then second part is that if it holds at any state, then it holds also in all next states. This is the inductive proof. Inductive proofs are very, very simple to prove using SAT-solver compared to other techniques, compared to symbolic model checking, BMC, symbolic simulation, whatever. So if we have an inductive proof, then we are actually happy because we get very quick proof. So then there is another fact, and if a property is provable, then this property can be how to say, can be done inductive, can be converted to be inductive. So in other terms, the property is always describing a set of behaviors. And if this property is proven, then this set of behavior can be reduced to a shorter set that corresponds to an inductive proof. So it means we can always shorten or strengthen the property to be inductive. If it is simple to prove it is inductive, if it is inductive. So the most challenging thing here is actually to find how we have to strengthen this property. And this is actually how to say the heart of the induction. And this is actually very how to say very active search topic today. And this is where leading to advancement in formal verification. So in the literature, you will find a lot of paper about this. There is different search groups, and there is at least two names for this research. One is called EC3, and the other called PDR. PDR stands for Proof Directed Reasoning. EC3 is inductive way to find this QX. I will explain it a little bit. So the idea is actually when you are done in the base case, you are proving that property holds for the initial state. Then for the step case, you are assuming property is holding for the step case, for the ones at any some states, and you want to prove that is holding for all next states. Doing this proving this, you could encounter a counter example, something which tells you that does not work. From this counter example, you will use some kind of solver to generate the QX. This is the idea. So this is the, how to say, the idea is just to look what is actually not working on the induction step, exploit this one, and generate from it what you are looking at, the QX. And then you have to restart from scratch and to see that the conjunction of what you have found as QX and with your property is inductive, and you repeat the same steps here, and you are done if there is no counterexamples anymore. This is a very how to say, very efficient. It uses not too much memory, and how to say, it's very effective for proofs. But for model checking, for firings or counterexamples, is sometimes bounded model checking is still better. Okay, so one thing is that I want still to mention here is actually for formal verification. If you are thinking about formal verification, you can write assertion or properties a little bit different than what we are doing in how to say, in simulation. Here's maybe 1 minute is not too much. Here's in 5 when you have a counterexample for the 5. What you are doing, you go to your design and say, okay, I have a trace showing a counterexample. Here's at this time I'm queuing some values. At this time I supposed to queue at the same time, but I do not see. There is a mismatch, and this is what actually you are showing to your designer, and this is what you want actually to have the tool telling you. This will not work with the simulation. What you have to do is, what you need is actually the time point. You have to model the time point. You can model the time point using some what we call non-deterministic input. It's something that actually is not related to the design, is floating, but from the formal verification tool is actually controlled by the formal verification tool. So, 2 slides.
Yeah, because we got everyone online as well, so you have to move to conclusion. So.
Okay, so
we need to move because everyone's waiting online as well.
Okay.
If you could just move to conclusion.
So actually, I want to say that this is exactly what I said about this way to debug the FIFO. You can write it using some what we call non-deterministic inputs. Something that you cannot do with simulation. This saves you a lot of states in the verification. So, okay.
Okay. Thank you. Thank you. Do you have any questions? Do you have any questions from Reading? Because if there's no questions, we'll move straight into the. You got a question? Okay. Cool.
Hi. A question on bounded model checking.
Yeah.
So let's say your design has 2 back-to-back counters. 2 counters, back to back, say, made-up design. When the bounded model checking says that this property doesn't fail until for 40 bounds, what does it actually mean? Does it mean, how does it traverse the tree? There could be multiple paths for your design to traverse 40 clock cycles. You could spend 40 clock cycles in the first counter, or 20 clock cycles in both the counters. What does it, does it
Yeah.
feedback?
So it's actually the depth that we are telling you that up to depth whatever the proof is the assertion is proven, or there is no counterexample. This depth is not related to any value, counter value. This is actually the number of cycles that you have to do from your initial state that you can unfold your transitions 40 times. Let's say this depth is n 40. You have to unfold your transitions 40 times, and within this 40 cycles, there is no counterexample. What is possible? Which possible values of the counters in this? It depends. So it can be any value. It can be only particular value that the other values are not reachable. But this is not coupled with this.
Okay, so thank you very much. We're in a